All right, so today we are going to be starting a new unit. We're starting the first of 4 trigonometry units. All right, so we're going to start off today with some of the basics. All right, basically, we're going to discuss a new way of measuring angles today. All right, so basically, everybody's familiar with degrees, right? That's how you've pretty much measured angles up to this point. All right, well, today we're going to talk about a new way to measure angles. All right, and it is called radians. All right, so degrees are just sort of arbitrary, right? Like sometime many years ago, somebody was like, yeah, let's break a circle up into a bunch of equal parts and call it something, right? Whereas a radian actually is based off of um, length, all right? So if we have a circle, can I make a nice circle? I bet I can. What's that? Right? I know, usually I definitely have to draw one. All right, so if we have a circle here, let's just do a line here. All right, and we've got this, which is obviously the radius. All right, so this is the radius r. All right, well, does anybody remember kind of what we call, like if I wanted to say this thing right here, this blue piece, does anybody remember what we call that?
Arc?
Yes, arc length. All right, so this is what we call arc length. All right, and for some odd reason, that's called S. Okay, arc length S. Okay, well, all right, so if you have some intercepting arc length here, all right, this is the Greek letter theta. All right, and it is used all of the time in mathematics to represent angles. Okay.
Just to have like a zero with a line through it?
Yep, pretty much.
Theta?
Yes, theta. All right, so it's kind of the x of angles. Okay, so in algebra, most of the time when we use a variable for something that we don't know, we call it x, right? Um, in trigonometry, when there's some angle, whether we know it or not, right, we call it theta typically. All right, so that just is an angle representation. All right, well, all right, when the arc length um, formed by an angle, and I'll call it theta, all right, is equal to the radius the angle has a measure of 1 radian. All right, so this may be kind of close, right? Up here, this is probably pretty close to this same distance here. All right, so we could say here that theta is equal to 1 radian. All right, so in general, all right, we say that an angle theta is equal to the arc length divided by the radius.
So in order for it to be 1,
Mhm.
the angle has to be equal to the radius.
No. The arc length. So the arc length formed by this angle theta. See how I have this angle? So this arc length up here would have to be equal to the radius here. Does that make sense?
Yes, sir. I was confused for a second. Like, how can the angle be?
Right, yeah. So if we look at this, and this is a kind of a rough approximation, but it looks pretty close to one radian. How many radians do we think are in one full circle, right? We know that one full circle is 360 degrees, but how many of these radians do you think would fit all the way around? Well, I might be able to do it kind of interestingly here.
Maybe 5.
It's not a bad guess. All right. So if I want to do probably can't rotate it is the problem there. All right. 5 isn't a bad guess. All right. So if we do have this here, so we'd have another one like here. All right. We could have another one like here. We could have another one here. So there's 4. There's 5. Yeah, I would say closer to 6. All right. Well, there's a way to actually figure this out. All right. So let's talk about one full revolution. All right, now we know that one full revolution, all right, is 360 degrees, but let's talk about it in radians. All right, so we know that it's S over R. All right, now, one full revolution, what is the arc length of one full time all the way around? What do we call that? What do we call the distance all the way around a circle? The circumference, right? So for one full revolution, my arc length is going to equal the circumference. What's the formula for the circumference of a circle? Does anybody remember? It's 2 times the diameter, or 2 pi r. All right. We typically do things in terms of radius a little bit more often. So it's 2 pi r for the circumference. Okay, well, then I can say that my arc length here is 2 pi r over r. What happens to my r's? They cancel. All right. So theta for one full revolution, there are 2 pi radians. All right. Well, what do we estimate pi at usually? 3.14. So this is roughly 6.28 radians. Now, you typically will see radians in terms of pi.
So that's how many triangles fit in?
Yes. Well, yeah, exactly. Like if you think of this kind of little wedge that we made initially, right? If you could copy it and keep like putting them in there, you would get 6.28 of those. Does that make sense? Okay. Okay. So we know that one full revolution, let's kind of move on here. All right. So one revolution Oh, come on. All right, is equal to 2 pi. All right, so what does that mean a half of a revolution would be?
Just 3.14.
Yeah, just pi. All right, so what would, well, I don't know, a fourth of a revolution be?
Half pi.
Yeah, half pi or pi over 2, which is the same thing as 1/2 pi. All right, we could obviously keep going. All right, what about an eighth of a revolution? Yeah, pi over 4. Yeah. All right, so let's talk about how to convert between degrees and radians. All right, well, and first we'll go from radians to degrees. All right, well, when you convert anything, right, you have to know some, how one relates to the other, right? You do this all the time in science class, right? So you're saying, okay, well, if you have something in inches and you want to put it in feet, right, you know that 1 foot is equal to 12 inches, all right? If you want to do something in yards and you have it in feet, right, you need to know that 1 yard is equal to 3 feet, et cetera, right? You have to have some sort of standardization between the two units, all right? Well, the easiest one to use here is this one, all right? So if a full circle is 360 degrees, what is half of a circle?
180.
180. All right. So we know that pi radians is equal to 180 degrees. Okay. Now, typically, whenever you're converting, whatever unit you want left, you put on top. All right. So all you have to do here is multiply by pi, oh, I'm sorry, by 180 over pi. Because we've just said that pi radians and 180 degrees are the same thing, correct? So anything divided by itself is 1. So if you multiply something by 1, you're not really changing it, right? We're just changing the units, all right? So for example, if I want to talk about, well, we can use this stuff over here just to kind of verify. Let's do pi over 4. All right. Okay, so we multiply this by 180 degrees over pi. What happens to my pi's? They cancel. All right, so really we're just doing 180 divided by 4, which is 45 degrees. So 1/8 of a revolution is 45 degrees, right? Well, that makes sense, right? If you have your circle, and you think right here, a quarter of the circle is 90 degrees, right? Well, half of that is obviously going to be 45 degrees. Make sense? Okay. So, oops, come on now. Yeah, you're going to put 180 on the bottom. Absolutely. All right. So, yep, easy to do. All right, so now if we want to talk about degrees to radians, all right, all we have to do is multiply by pi over 180. All right, so really all you have to remember is whatever you're trying to get to goes on top. right? So if you're trying to get to degrees, degrees goes on top. If you're trying to get to radians, radians goes on top. Okay, so if we look at another example here, all right, let's just start off with, oh, I don't know, 60 degrees. All right, so we multiply this by pi over 180. Well, here my degrees will cancel, right, which just leaves me with radians, which is what I want. All right, well, 60 over 180 can be reduced. 60 goes into both of these evenly. 60 goes into 60 once. 60 goes into 180 3 times. All right, so this is actually going to be 1 pi, or just pi, over 3. And although this is radians, you never really have to write radians, right? If it's given in terms of pi, it's typically understood that it's in radians. Okay, so you don't really ever have to worry about writing the word radians. Everybody good so far?
Yes, sir.
Cool. All right. So the next thing that I would like to talk about here are coterminal angles.
We're probably gonna have time to discuss that.
Yeah, should. All right. Now, the first thing that we need to talk about before we get into coterminal angles are just kind of the basics of angles in general. All right. So we know an angle is produced by two line segments or two rays, right? And we'll just call this angle theta. All right. Now, in math, all right, the kind of direction actually matters. All right, in any angle, we're going to have a few pieces here. All right, we're going to have what's called the initial side, which is where you start from. And you're going to have what's called the terminal side, which is where you end. All right, so, and that's why I put the arrow right here, because I started down here and I'm going in this direction. Okay. Now, in math, we typically talk about angles in what's called standard form. All right, and I wish kind of math and science would one day just get on the same page. All right, but it's actually like very different than how science does it. So, I mean, not very different, but it's oriented differently. Okay, so if we think of our typical, X, Y coordinate grid, okay, in standard form, the initial side is always the positive x-axis. So we're always going to start from here. All right, so I'll just do some arbitrary angle here. All right, so angles can also be negative or positive. All right, yes. All right, if we go counterclockwise, we say that the angle is positive. All right, so obviously if we go clockwise, we say that the angle is negative. All right, so in this case, because I'm going counterclockwise, this would be a positive angle. All right, so we could say here that theta is equal to, that's probably about 135 degrees. Which would also be 3 pi over 4 if we're talking radians, which we could have just used our conversion to get that. Eventually we'll get a lot better at that, and we'll talk about the unit circle tomorrow, which we'll get into a lot of these angles and a lot more specificity. Okay, so, but we could also say that that exact same angle, if we go this way, all right, yeah, so we could say that that is negative 225 degrees. All right, because here's 180 and then about 45 more. All right, so as you can see, this same angle can be named two different ways as far as the same initial and the same terminal side. All right, now, like we said earlier, when we talk about angles in standard form, which in math, that's pretty much what we're kind of always going to be doing for the most part. All right, so we always have the positive x-axis as my initial side. All right, so I can get to this same terminal side by either coming 225 degrees in the negative direction or positive 135 degrees. All right, well, since we have the same initial, of course it's standard, and the same terminal side, these are called coterminal angles. They're coterminal to each other. Every angle will have coterminal angles. It'll just be different. Now, if you add the absolute value of these together, what do you get? The absolute value. So think of this as positive. What's 225 plus 135? 360, right? So coterminal angles, if you add their absolute values together, will always be 360 degrees. All right. When we're talking about small angles like this. Okay, now, is this the only two ways, negative 225 and positive 135, that you could name this angle? Or are there possibly more? All right, well, what if I start here, go all the way around, so how far have I gone? 360, and then I keep going, and I stop here again.
360 plus 135.
Yeah, exactly. 495, yeah. So this theta can be 495. All right, which is also a coterminal angle. Could I start here at my positive x-axis, go all the way around twice, and then come here and stop again? Sure, I can. All right, so how many coterminal angles does any angle have? Infinity. Okay, so to get coterminal angles, all right, simply add or subtract 360 degrees, right? Or 2 pi, if we're talking radians, right? Because 360 degrees and 2 pi are the same thing. And you can do this infinitely. Right, and going back to our example here, right? If we started with 135, well, if you add 360, you get to this 495 that we got to. If you subtract 360, you would get to this negative 225. And you can just keep doing that as many times as you want, right? So every angle has infinite coterminal angles, all right? So we'll just put an example on here. All right, let's go find one positive and one negative coterminal angle for both. Let's go 240 degrees and we'll go 16 pi over 3. Okay, so for 240 degrees, that's easy. All right. How can I get my first coterminal angle? Yeah, let's add or subtract 360. So if I do 240 plus 360, what do I get?
600.
Yep. All right. If I do 240 minus 360, what do I get? Negative 120. All right. Is one of these positive and one negative? Yeah, then I'm good. All right, I've done what was asked. All right, so now let's talk about 16 pi over 3. All right, well now instead of adding and subtracting 360, what am I doing? I'm adding or subtracting what?
2 pi.
2 pi, yeah. So here, let's go 16 pi over 3 plus 2 pi. Now, what am I going to have to do here?
Put a 1 over.
Yeah, we want this as a fraction, and then we're going to have to find a what? Common denominator. All right, so this is going to be 16 pi over 3. I want this to be a 3, so I can multiply both the numerator and denominator by 3, and that becomes 6 pi over 3, right? We all agree that this would reduce to 2 pi?
Yep.
All right, so here we would just get 22 pi over 3. All right, well, let's subtract. So we get 16 pi over 3. We're subtracting 2 pi, which again is 6 pi over 3. So what do I get here? Yeah. Now, we did indeed find two coterminal angles, right? But is one positive and one negative?
No.
No. So what do we have to keep doing? Yeah, we have to keep subtracting until we get to a negative number. All right. And this is, I always ask this exact same question on the test. I mean, not these exact same numbers, but where you have to find one positive and one negative. And I can't even count how many. I mean, I would say it's close to 50% of students just on this problem here would just stop right here.
So then you just have to give 2 more times, right?
Mm-hmm.
So then you get negative 2 over 3, right?
Yep. So if you subtract 2 pi again, you would get 4 pi over 3. That's still not enough. So you subtract 2 pi again, and you will get negative 2 pi over 3. All right, well, now we have a negative and a positive. Now, if you kind of notice before you even start that this is way bigger than 2 pi, honestly, you could use this as a positive coterminal angle, or you could have used this as a positive coterminal angle. Do you know what I mean? So we actually found 4 coterminal angles here, right? But any one of these 3 would work as the positive one, and then of course we would need this one as a negative one. Fair enough? Okay. Okay. So we just talked about that, so I'm going to skip that. Okay. So go ahead and take a minute to convert these to radian measure. All right. So of course, if you remember, to convert from degrees to radians, we simply multiply by pi over 180 and simplify.
For 230, what do you get? Over 3 pi over 18.
Yep. Okay. So let's go ahead and take a look at these. All right, so all we're doing is multiplying by pi over 180. All right, of course, you can always cancel these out. So now you're left with 6 pi over 18. Of course, 6 goes into 18 3 times, so that's 1/3 pi, or just pi over 3. All right, we do the same thing here. Multiply by pi over 180. Of course, we can cross these out. All right, 32 over 18. All right, 2 goes into this 16, 2 goes into this 9. So 16 pi over 9. All right, and then here, again, we're multiplying by pi over 180. So of course these will cancel. This doesn't reduce at all, so this is just 23 pi over 18. Good times?
Do we have to put radians or not?
No. Especially when it's in terms of pi. Basically, whenever you're talking about, and you will get to times where you'll see some radian measure that's not in terms of pi, like you'll see like 2.1 radians, right? Anytime that it does not have a degree sign, it's just implied that it's radians. Like it doesn't, in order for it to be degrees, it has to have that degree symbol. If you ever see an angle, like if you're given an angle measure and it doesn't have the degrees, it just means it's in radians. Okay, so now let's go the other way. All right, let's go ahead and convert radians to degrees. And it's all Kelsey's fault today. I don't know what it is. I don't know what's your fault, but whatever goes wrong today, we'll blame on you. I know. It's kind of mean, but sometimes you just gotta place blame, you know? Back before COVID, I used to always have somebody in each class like assigned a day. Like every Monday, anything that goes wrong is your fault.
Oh, yeah.
Any Tuesday, anything that goes wrong is fault. You know, like, and I just used to do that just for fun. Usually it was my smartboard that would mess up, so I had to blame it on somebody. I always took Fridays. Fridays were always my fault. Because everybody likes a Friday.
Fridays are good.
Yeah, Fridays are good. Well, especially hybrid. I'm gonna miss Fridays.
So then when it says 3 radians.
Yeah, like it's not in terms of pi, but you still multiply by 180 over pi.
So you just get
540 over pi degrees. Yeah, I know it's not aesthetically pleasing, right? Okay, so here we're trying to convert to degrees. So we are multiplying by 180 over pi. So here the pi's cancel. 180 divided by 6 is 30. So 30 degrees. 5 pi over 3, again, we multiply by 180 over pi. My pi's again cancel. All right, 180 divided by 3, all right, is 60. And then if I multiply that by 5, 60 times 5 is 3. What's that? Should be 300, right?
I'm talking about 180 times 5.
Oh, yeah, okay. Yeah, 900 divided by 3 is
Yes,
300, yeah. All right, and then as we just discussed, right, this is not aesthetically pleasing because it's not in terms of pi. We typically like radian measure to be in terms of pi, all right, but it's fine. We just have to do this. All right, obviously pi doesn't cancel with anything here, and 3 times 180 is 540. So this would just be 540 over pi degrees. And that's really all we can do without a calculator, right? If it said, you know, with a calculator, then you would go ahead and plug this into your calculator, and you would get 171.887 degrees. All right, so, but it said not to use a calculator, so we just leave it as is. Okay, So now, if possible, find the complement and supplement, all right, of each angle. Okay. Now, remember complementary angles, all right, they add to 90 degrees, all right, or pi over 2 radians. All right. Supplementary angles add to 180 degrees or pi. We're talking about radians. Okay, so do keep in mind, all right, that when you're trying to find, excuse me, when you're trying to find complements and supplements, all right, you can't use a negative angle to form a complement or supplement. Okay, they have to be positive. All right. So here for 15 degrees, all right, the complement, all right, well, 15 plus 75, all right, would add to 90.
Oh, that's easy.
Yep.
And then 165.
Uh-huh. Super easy. Okay. Here, complement, we would actually say there isn't one, right? Because I just said we can't use negative angles here, right? And there's no positive number that you can add to 152 to get 90, all right? It does, yep, it does have a supplement, however, which is indeed 28 degrees. All right, so now we'll talk about some radian measure here, okay? Now, it's also, we were able to do these in our head very quickly, right? But really, how you would think of it mathematically, right? To get the complement, you do 90 minus this angle, right? That's how we got 75. And to get the supplement, you do 180 minus this number, which is how we get 165, right? Now, of course, with degrees and basic addition and stuff, we're pretty quick in our heads just be able to do that. All right, now with radians, all right, in terms of pi, it's not always quite as cut and dry. All right, so here, instead of doing 90 minus this, since we're in radians, we're going to be doing pi over 2 minus this. All right, so to get the complement, we say pi over 2 minus pi over 6.
So they're going to be negative?
Nope.
No.
Mm-hmm. So we need to find a common denominator here, right, which is obviously going to be 6. So I can multiply both the numerator and denominator here by 3, and we get 3 pi over 6 minus pi over 6.
Oh.
Right. And so this would be 2 pi over 6, which actually reduces to pi over 3. Right, and similarly with the supplementary angle, now we're doing pi minus pi over 6. Of course, we want a common denominator again, so we're going to have 6 pi over 6 minus pi over 6, and that's just going to be 5 pi over 6. All right, go ahead and try this one now that we've kind of seen how to do it with radian. Right. All right, so to find our complement, we do pi over 2 minus our angle. All right, we're going to have to get a common denominator here again, so we will get 3 pi over 6 minus 5 pi over 6. All right, now this will give us a negative, all right, which we can't have, so we would just say there is no complement. All right, the supplement, we do pi minus 5 pi over 6. We actually kind of basically did the opposite of that right up here, right? If 5 pi over 6 is the complement of pi over 6, then obviously pi over 6 has to be the complement to 5 pi over 6. Yeah. So, good times there. Okay. So, now we're going to talk a little bit about arc length and the angle that intercepts them, etc. All right. You have some of these on your delta math. And so let's do a circle. All right, so it tells us here that we have got a circle with a radius of 27 inches. Alright, so I know this is 27 inches. Alright, find the length of the arc intercepted by a central angle of 160 degrees. Okay, so we can just estimate this at 160 degrees, and we want to find this. Alright, and this is S. Now, there's a couple of different ways that you can do this. These are also questions that are notorious for being on SAT and ACT. Right? You almost always see something like this on the SAT or ACT. All right. There's a couple of different ways that you can do this. In terms of kind of how we've been talking about it, you could just convert 160 degrees to radians. Yeah, so 8 pi over 9. All right, and then you could use kind of our formula for definition of a radian, right, where theta is equal to S over R, where S is the arc length and R is the radius. Well, if we're trying to solve for S here, right, couldn't we just multiply both sides by R and say, okay, well, the arc length is equal to the radius times the angle. Okay, now this only works when it's in radians. That's why we had to convert it to radians first, because we're literally using the definition of a radian here. Okay, so do kind of keep that in mind. All right, so here we just say, okay, well, 27 times 8 pi over 9. All right, 27 over 9 is just 3, right? 3 times 8 pi is 24 pi. So this would be 24 pi inches. Okay, so that's how you can do it kind of in terms of radians, all right? There's another way that you can do it, leaving it in degrees, okay? So we know that the arc length of the entire circle is just the circumference, right? And so I know the circumference is 2 pi times r, which in this case is 27. All right, and now all we have to do is set up a proportion, right? Well, this is 160 out of 360, right? So all I have to do is say 2 pi times 27, and then multiply that by 160 over 360, which is just the proportion of the circumference. Does that make sense? All right. So we could do that here. Of course, the math's a lot harder here, right? course, you can simplify this a lot. All right, so this is going to be 54, and then this is going to be, let's see, 8 over 18, so 4 goes in there, so 4/9. All right, so 9 goes into 54, 6 times? So 6 pi times 4, again, is 24 pi. All right, so either way, you're going to get there. And either way is a perfectly legitimate way of getting there. Cool beans? Okay. Okay, so now we're going to talk about linear speed and angular speed. Okay, so angular speed, which I will just call AS, all right, is literally like as something is moving around a circle, right, like a clock hand is a very good example. How fast is the angle changing? That's what angular speed is, okay? In angular speed, the formula is really easy. All right, all we have to do is say some angle divided by some amount of time. So, radians per second, degrees per second, depending on what you're given. All right, now, linear speed, which I will call LS, right, is, say you're standing on say there's a giant massive clock, right? And if you're standing on the end of the second hand as it's moving around, how fast are you actually moving, right? And that, of course, is some measurement of speed, so some unit of distance divided by some unit of time, right? Feet per second, miles per hour, meters per second, whatever. Okay, so in order to do that, all right, we have to have some length, which really we think of the arc length divided by some unit of time. Of course, we just talked about the arc length actually being r times theta. So if you notice, these two formulas are very similar. The only difference is you're multiplying by r. Now, for linear speed, since you're using the definition of a radian, all right, this must be in radians. If it is in degrees, you will be very wrong. Okay, so this question here, they ask us to find the linear speed. All right, it says the second hand of a clock is 8 centimeters long. Find the linear speed of the tip of this second hand as it passes around the clock face. All right, so I'm using this formula here. Angular speed is equal to r, the radius would be 8 centimeters. All right, now we need to know some theta. What's a really easy way to talk about second hands, right? Well, I mean, you could do it like how many radians has it gone in half of a minute, or in 15 seconds, or 10 seconds. But why do that, right? Why not just say, how long does it take for a second hand to go all the way around the clock? 60 seconds, right? So the theta, how far is one full time around a circle? 2 pi, because it has to be in radians, all right, divided by how long did it take for that second hand to go one full time around? 60 seconds. All right. Of course, this here is in centimeters, and this here is in seconds. All right. So, of course, this will be 16 pi over 60. All right. 4 goes into this evenly, right? So 4 pi over 15, and this would be centimeters per second, right? Because I have centimeters up top, seconds in the bottom, centimeters per second. All right, now, that really doesn't help us any, right? Like, imagine if you were driving down the street and you saw a speed limit sign, right? And it said 32 pi over 4 miles per hour, right? You're going to be like, how fast am I allowed to go? Right? Like you're not going to see 34 pi over 3 or whatever I said it was, right? And be like, oh, I know exactly how fast I can go. Okay, so in this case, this would be on a calculator portion. So we would want to say, 4 pi divided by 15, right? So that's 0.838 centimeters per second, right? That makes a little bit more sense in our head, right? So, okay, we're going a little bit less than a centimeter per second. Fair enough? Yes, these are easy if you know the formulas. All right, so here, the circular blade on a saw rotates at 2,400 revolutions per minute. Find the angular speed of the blade in radians per second. Okay, well, angular speed we know is simply theta over t. It wants it in radians. All right. Now it says that this thing goes 2,400 revolutions per minute. All right. So 2,400 revolutions in radians. What is one revolution? 2 pi. Right? So we're doing 2,400 times that 2 pi per minute. Now, it wants this in radians per second. How many seconds are in a minute? Yeah. So here you just say 60 seconds. All right. So we go ahead and simplify this. All right. Let's see. Those will cancel. 24 divided by 6 is 4, so that's 40. So this is going to be 80 pi radians per second. And since we're talking about radians, it's perfectly acceptable to just leave that in terms of pi. And we typically like radian measure in terms of pi. Nope.
The only one that I'm confused about is like the when we did the radius of 27. Just because, like, how do we get 245 when we did 27 times 8 pi over 9?
When we did 27 times 8 pi over 9.
Yeah, you got 245.
It shouldn't be 8. 40. Okay, so 20. It should be 40, just 45, right? Because 27 divided by 9 is 3. And 3 times 8 pi is 3 times 8 is just 24. So it should just be 24 pi. Which one was that, Mom?
One is the radius.
This one?
Yeah.
Yep, 24 pi, and that little, that's just inches.
I thought you said 245, so that's why.
Oh, I got you. Nope, just 24 pi.
Thank you.
Yep.
I got it now.
Cool beans?
Yes, sir.
Right, so when I said pi, you thought I said 5. Gotcha. Okay, so here it says the blade has a radius of 4 inches. Find the linear speed of a blade tip in inches per second. All right, so our linear speed is equal to r times theta over t. Well, it tells us that the radius is 4 inches. All right. Again, this theta is the same theta as up here, right? And it told us that it was doing 2,400 revolutions per minute. We said that one revolution is 2 pi. So this is 2,400 times 2 pi. Again, per second, it told us one revolution per minute, and we know that there are 60 seconds in a minute. All right, so 2,400 divided by 60 is going to be 40. 40 times 4 is 160, times 2 is 320, so 320 pi, and that's going to be inches per second. Of course, again, linear speed, pi doesn't help us very much, right? You can't really visualize how fast that really is. So if we say 320 pi, that is 1,005.310 inches per second. So over 1,000 inches per second. That's pretty fast, right? Which makes sense if you're on like a saw blade that's flying around very quickly. Okay, that is it for the day. You can go ahead and stop.